So we have been discussing about this biomimicking based structures and biomimicking based robots, micro robots. So in that we have been discussing about the biological based systems, like how these biological based systems are mimicked with reference to biomimic perspective point of view. And we have also discussed some of the applications, the relevant applications, how it has been evolved. Okay, so like we have been discussing about the bacterial base, and with reference to bacterial base, we were focusing more on the micropropulsion perspective point of view. With reference to micropropulsion, we have categorized the different micropropulsion mechanisms which are being evolved, and how these micropropulsion mechanisms are being effectively used for different functional applications. Like in the other words, like we can also, now we will discuss about this micro drones. In fact, in the last module we had discussed more on these micro drones. In most of these micro drones, so we were focusing upon the different micro actuators which are deployed, the micro sensing elements which are deployed, how these micro actuators and micro sensors are catering the different applications or as well as suitability. Okay, now in today's lecture, so we will discuss about a kind of a micro mechanical flying insect, how these, because like with reference to micro drone perspective point of view, so we are going to use a micro motor or a certain amount of micro actuation mechanisms. But when we try to see a honeybee, or when we try to see a kind of a small fly which is moving, so and it is easy, it would be better that if we can look into the mechanism of how these flight motions are being generated, and what are the mechanisms are being deployed, and how these mechanisms can be replicated appropriately for different applications. Okay, so in this particular module, so I will be discussing about one of the key case study, which is a kind of a micro mechanical flying insect. So as far as these micro mechanical flying insects are concerned, so these micro mechanical flying insect is a miniature UAV which is composed of a metal body with 2 wings and a control system. So this micro mechanical flying insect, which is aimed to create a kind of an autonomous flying robot insect with almost the size of a housefly. So to do this, like biologists have identified the mechanism in the real insect which is necessary for especially for the flight, thus solving the mystery of how insect produce an adequate lift for stable flight. The result that shows that to produce an enough life while also having a structure which is capable of creating a thrust vector necessary for control of the insect. There are number of key kinematics and dynamics requirements which are there. So when we try to talk about this MFI, the MFI wing must have a capable of independently going through the wing stroke of around 120 degrees while being able to rotate at 90 degrees at a resonant frequency. So if we try to list out the process parameters which are evolved, so one is with reference to the wing stroke of 120 degrees and a resonant frequency of 150 hertz. So to do this, the body of this micro mechanical flying insect consists of 2 wings, each driven by a separate thorax structure. So if you look into this mechanism of this particular structure, so there is a kind of an airframe is there. Then there are 2 actuators which are being placed. Then there is a kind of a slider crank mechanism which has a kind of a small micro 4-bar chain mechanism. So we have a wing kind of structure, and then there is a differential structure which is available. So the main function of the differential structure is for the movement in a forward and a return stroke, and the wing take care of the flapping mechanism over here. So here the resonant frequency which is expected is close to around 150 hertz, and the wing shape has a degree of close to around 120 degrees, and it has a ability to rotate at 90 degrees. So to do this, the body of this MFI consists of 2 wings which is shown over here, each driven by a separate thorax structure. So this thorax structure consists of two actuators. One is a kind of a mechanically amplifying 4-bar structure, and the other one is a kind of a differential structure. So since the as far as the main focus of this particular structure is the kind of air is a propulsion to the velocity of the wing squared. So the most important requirement are the high resonant frequency and the large stroke angle. So one technique for the construction of these micro robots used micro machined silicon for linkages and hinges. So considering the material as silicon, so it is of lightweight and it can be effectively used for joints. Next, with reference to inertial perspective point of view, we may need to discuss about the overall how these resonant frequencies can be effectively used for this inertial mechanism. So this also give rise to a higher mechanical Q, causing to a decrease in the controllability. So here in this particular case, so we will be discussing about the degrees of freedom involved on the overall one axis of this thorax structure, and as far as material perspective point of view, so we have a kind of a carbon fiber based structure in place. So a kind of a composite wing with a composite airframe. So to keep the weight low, these MFI uses a kind of a structure which we call it as unimorph based structure. So these unimorph based structure, so basically it's a kind of a piezoelectric integrated structures. So such actuator basically produces a large forces and it provides a small displacement that is necessary to use a kind of a mechanical amplifier to the stroke. So there is an option like these actuators, either it has a stainless steel based structure, or in certain cases it can also have a kind of a silicon based structure. So by utilizing a high stiffness to weight ratio of composite, these inertias can be decreased by allowing of tailoring this anisotropy layer. So these anisotropy makes it possible to create an actuator with a kinematic property which allows the simplification to be made with the kinematic of this 4-bar structure. Now when we try to look into one of the key challenges which are involved over here is the kind of a microfabrication. So when we closely observe the microfabrication perspective point of view, so the first important consideration is the fiber reinforced material for construction of micro devices. So this link with the 4-bar structure having a size which is ranging from 0.5 mm to 6 mm is the length, with the width of 0.5 mm to 1 mm. This is the length and this is the width. So for such kind of these honeycomb structures, using a cell wall size of the order of magnitude less than the smallest dimension with a thorax which gives a kind of a 50 micrometer as the smallest reciprocation which is being deployed. Now when we try to look into the required beam width or for these fiber reinforced composite with fiber diameter of close to around 10 micrometer, this approximately limits the size of the material. So using composite of these application, it assumes it has the ability to machine the laminates as a single ply basis by ply basis down to accuracies and approximate the fiber diameter. So the traditional method of cutting and handling these material is not possible at this scale. Instead, a laser micromachine stage is used to cut the plies both in a cured and at an uncured state. To this, all plies are designed using a two-dimensional CAD package and a laser cut and the plies automatically. For example applications, the material with high stiffness to weight ratio was desired with a carbon fiber reinforced epoxy. So experimentally, up and down cured plies can be cut simultaneously or one or more uncured plies. To eliminate the errors during the construction of the cut laminate, all angles are controlled with 2D CAD layout and the plies are aligned visually under a microscope before cutting. So one of the major concerns of this laser micromachining is like these laminates is whether to cut the composite cured or the uncured. Using uncured layers like to construct the thorax has a greater benefit of being able to lay up the laminate for the link and a polymer for the joint at one particular time. So these cured laminate without the needs of extra adhesive layers can be deployed. This simplifies the construction and cut down the inertial by eliminating the need of an additional epoxy. So when we try to look into the micromachining behavior, so these are some of the kind of a laser micromachined structure with a phase sheet and a honeycomb section and a molded honeycomb layer. These laser micromachining and uncured lamina has difficulty since the laser creates a kind of a localized heating, causing the epoxy matrix to flow around the cutting area, causing the laser to go out of focus. Thus, the laser cutting uncured lamina is possible, but it becomes increasingly more difficult with smaller part size, and it is only possible for one layer at a time. Also, since the uncured matrix is still in a viscous state, smaller features can be easily destroyed in handling after cutting. Through a careful practice and paying attention to these problems, so these MFI thorax has evolved to use in a construction. Basically, it depends upon the mostly uncured layer. Okay. Now, let us see the overall construction or the kind of a composite laminate which are being established over here. So in this particular structure, if you see, so we have the actuator in place, and then there is a kind of a 4-bar mechanism, and then there are a kind of a multiple composite link with flexures which are being incorporated over here. So these flexures along with the composite link and the actuators will cater the overall like flow of the structures what we are looking for. Now let us discuss about the overall like parameters which are involved for such kind of composite link. For the maximum weight saving, the beam should not be a kind of a solid structure, because like as far as in this particular case is concerned, so the overall parts which are involved or the overall structures which are involved are going to play a vital role with reference to the deflection perspective point of view. So like when we try to derive the relation for a composite link, so for the maximum weight saving, the beam should not be a kind of a solid structure. Instead, a honeycomb configuration can be used, and the analysis done for the beam is aimed at matching the stiffness of the stainless steel beam while minimizing the weight of the beam. So first, the stiffness of the double supported cantilever is given by K equals 48 EI by LQ. So the current beam has a kind of a triangular cross section with a moment of inertia which can be represented as I of T equals √3 by 96 B power 4 minus B TS the for 4. So the cross section moment of inertia of the honeycomb structure can be considered as IH1 equals half 1 by 12 BH cube minus small BH cube. So if we try to look into the since we are considering a kind of a triangular cross section, so these triangular cross section can be nomenclated as the larger b, smaller b, and this is the H. This is the thickness of a wall. This is the H, and this is the B. And again we have the T wall and the T base which are being available over here. So here in this particular application perspective point of view, so here this is a kind of a elastic layer and the piezoelectric structure which is being considered as an actuator. So this is a kind of a unimorph structure where one way of actuation is taken care by the piezoelectric structure and the return stroke is taken care by the elastic layer which is available. So appropriately the actuations are controlled and the actuations are appropriately translated to the slider crank mechanism with the 4-bar and the wing kind of arrangement. So this is a kind of a model which basically caters the kind of a 1 degrees of freedom which are being experimented. Now when we try to look into the cross moment of cross sectional moment of inertia, we have IH2 equals BTF TC squared by 2. So TF is the face thickness, TC is the core thickness, and the stiffness of the beam can be represented as 3.6 into 10 power 5 Newton per meter. So if it is approximately, if you try to calculate the overall weight of it, it is close to around 1.4 mg. Now one of the major challenge which are involved is with reference to this joint fabrication. So this 4-bar constructed by the sandwiching the polyester flexure layer with the honeycomb structure. So there is no need for a clamp to prevent peeling, as in this case the kind of a steel beam structure, the final element of this one DOF thorax is the connection between the actuator and the base link. So since the actuator tip and the base link slider crank is attached to the point, it forms a 2 intersecting arcs and there is need to go for an additional joint between the 2. So this is achieved using a kind of a traditional slider crank mechanism, and the current like a MFI thorax uses a kind of a slider crank which relies upon the buckling strength of the flexures to determine the serial stiffness. So because of the nonlinear motion of the actuator and the 4-bar base link, this design causes a kind of a nonlinear decrease in serial stiffness, in effect creating a kind of a backlash element. This eliminates this kind of a no buckling design which is a kind of an introduced. So when you try to look into the kind of a concept which is established over here, like this is a kind of a slider crank which increases the serial stiffness by ensuring that regardless of the position of the element of the thorax, there will be a flexures within the slider crank that are in tension. This concept has been attempted by using a standard steel beam construction. However, it is ineffective using a kind of a using the construction which is in a bulky which is in the form of a bulky or in the required where there is a kind of a too complex structure which exhibits to obtain the link with the required stiffness. So the stiffness of the slider crank must be higher than the rest of the thorax links, since the slider crank will see the highest force. Also, the complexity of the structures causes alignment errors to arise, leading to a kinematic singularities and an increase in the effective parallel stiffness. Thus, if the stiffness of the sections could remain high while using a planar structure to decrease the complexity, the no buckling slider crank could be made in small and in the efficient form factor. So ideally, so these are some kind of concept for with reference to no buckling perspective point of view. Now, like if you observe in this particular figure, where there is a kind of a model of the completed 1 degree of freedom, the results of the carbon fiber, this MFI thorax, are compared to the results from the kind of a steel version, where with the which are affected by the lower inertia and the reference frequency are considered to be one of the key aspects which we may need to look into it. Now, when we try to look into the overall description, so or with reference to design and structure perspective point of view, when we look into the biomimetic approach, these MFI mimics the flapping wing and a kinematics of insect. Especially there is a insect called Diptera, which is a kind of a fly which is known for their highly maneuverable flight. It uses two independently actuated wings like a real insect, enabling a complex flight pattern such as hovering and quick return and stabilization. When we try to look into the material and fabrication perspective point of view, it is built using a kind of a micro electromechanical system technique. So in fact, we have discussed about the laser fabrication which are being evolved, which takes care of, which enables a precision at a small scale. So the primary material basically includes a kind of a carbon fiber composite for structural strength with minimal weight, a polymer based flexible hinges to replicate insect wing joints, a thin film piezoelectric actuator to generate a motion of a wing flapping. Now, when we closely observe the wing mechanism and actuation, unlike traditional rotary propellers, these MFI flap its wings using a kind of a mechanical transmission system. In fact, the overall mechanism of this mechanical transmission system we had discussed, where there is a kind of a 4-bar chain mechanism which is there for this flapping arrangement. The flapping motion is driven by a piezoelectric actuator which converts electrical energy into a mechanical motion through a deformation of a piezoelectric material. When we look into the flight mechanics and aerodynamics perspective point of view, these flapping wing kinematics, the insect uses a unique mechanism where wing moves in an elliptical or a figure 8 pattern to generate the lift and the thrust. These MFI replicate these kinematics to maximize their lift production, basically a kind of a low Reynolds number, so that these caters the insect scale aerodynamics. It also reduces the power consumption by utilizing a passive wing deformations. When we try to look into the overall lift and the thrust generation, at small scales, traditional aerodynamic fixed wing or propelled base systems are inefficient. So this MFI relies on an unsteady aerodynamics such as delayed wall structure, where the wing remains at a high scale of attack without stalling and an increasing lift. A rotational lift, the lift is enhanced due to wing rotation at a stroke reversal. A wake capture, where the energy from a previous stroke is recaptured for efficiency. Now, with reference to stability perspective point of view, so this MFI it's a kind of an independent wing control. It allows it hover in place like hummingbird or insect. It performs a quick turn by altering wing as with reference to stroke and amplitude phase, and it maintains a stability in the turbulent environments. With reference to actuation and power system perspective point of view, these actuators, it uses a piezoelectric actuator instead of a traditional motor due to a size and the weight constraint. These piezoelectric material expand and contract rapidly. When voltage is applied, it generates a kind of a wing motion to the system. When we try to look into the power supply perspective point of view, these current prototypes are tethered to external power source but future iterations aim to onboard power solutions including high energy density micro batteries, energy harvesting from ambient source. Some of the energy sources basically includes the solar and the RF energy. When we try to look into the control system perspective point of view, so to achieve these autonomous flight, the MFI must integrate a lightweight high-speed sensor such as optical flow sensors for motion detection and navigation, gyroscope and accelerometers for stability and orientation, bio-inspired antenna or tactile sensor for environmental awareness. When we try to look into the feedback control perspective point of view, flight at such small scale requires high-speed feedback loops to adjust the wing kinematics in a real time. It has a control strategies which includes the proportional integral derivative controller for maintaining a stable flight, a neural network based adaptive control for mimicking the insect reflexes. Some of the key features of these MFI is like it has a kind of a flapping wing mechanism. So ideally it uses a kind of a piezoelectric actuator owing to the requirement of high frequency actuation or other micro actuators to drive the wing motion. Mimic insect wing kinematics to generate the lift and the maneuverability. Miniaturization and MEMS fabrication. It is constructed using a MEMS based lithography technique. So the components are designed at the millimeter scale with typically a few centimeter in size. It has a high wing beat frequency. It operates as a wing beat frequency like real insect close to around 100 to 200 hertz. It also achieves a rapid thrust and agility. So it has a kind of a lightweight structure. It is made out of a lightweight material like carbon fiber and a polymer composite. It also allows for efficient power to weight ratio. It has its own autonomous control challenges which requires a kind of a high speed feedback control for stability, like when there is a kind of a frequency with reference to a lift and a drop. So this feedback should be appropriately fed in such a way that the response time is quite high and then immediate actions can be taken. So however, the current research is more focused towards integrating an onboard sensor, and it is widely used for some kind of energy sources as well as the energy like management related applications. Some of the key challenges which are evolved with respect to this MFI perspective point of view, like a kind of a miniaturized power supply. So developing an onboard power source which remains a major challenge. And second thing is autonomous control. Real-time flight stabilization and navigation requires an advanced microprocessor and an AI-based control for such kind of autonomous control. Manufacturing precision perspective point of view, these MEMS fabrication needs to ensure a high precision even at sub-millimeter scale. And environmental factors perspective point of view, these insert scale aerodynamics are highly sensitive to wind and turbulence. When we try to look into the future directions, so there is a huge scope towards wireless power solutions, inductive charging or ambient energy harvesting system. It is also used for an advanced AI for autonomous navigation, machine learning for real-time decision making, swarm robots, a kind of a coordinated movement of multiple MFI for complex tasks, improved material like development of lighter, more durable material for longer flight endurance. So these are some of the key challenges which will be focused. Okay. So in the next class, we will be discussing about the algae based micro robots, and we will also discuss about like these water striders, overall mechanism involved in water striders in detail.